Now we will revisit all the three cases we discussed last week. The first one is Lipschitz continuous case. Second one is smooth, beta smooth. The third one is beta smooth and alpha strongly convex. For the first case, we define x bar, and with x bar, the convergence rate of convergence was 1 over square root t. For the smooth case, when we set gamma is 1 over beta, we have 1 over t learning rate, the convergence rate. The third one, when we have beta smooth and alpha strongly convex, then and when we set the learning rate or step size equal to 1 over beta, then the learning rate is linear, so exponentially converges to the optimal point. Okay. So from the result, we will expand the result to the case where the constraint set exists. So every time we have to consider the projection step. Okay. Fortunately, at least for the first case, we can say almost same result. When we define x bar as before, then fx bar minus fx star is less than or equal to RB over square root capital T with this step size. And this result is exactly the same with the unconstrained z case. Okay. So let's recap the original result without any constraint. Okay. So how to bound fxt minus fx star. So from the elementary identity the elementary equation, we have this analysis fxt minus fx star is less than or equal to gamma over 2 times gradient of fxt norm square plus 1 over 2 gamma times xt minus x star square minus xt plus 1 minus x star square. So sum this up over the iterations, then we have this. Okay, and since this one is positive, so this in total negative, so minus positive, so this is negative, so we can simply ignore because we just want to upper bound this summation, so we can ignore this. And since we assume that the smoothness, Lipschitz continuity, so from the Lipschitz continuity constant, we can upper bound this one as well. Okay, we can upper bound this one by b. Right. So that was the main technique for the Lipschitz continuous case. So as before, we can do almost same proof. So from the convex property, we have fxt minus fx star less than or equal to gradient of fxt transpose xt minus x star. Okay, so now the difference compared to the previous, the unconstrained cases, we have ft plus 1. And no, yt plus 1. And yt plus 1 is xt plus 1 for the unconstrained case. Okay. So up to this point, it is okay because there is no difference compared to the unconstrained case. And using this trick, 2a transpose b is equal to a norm square plus b norm square minus a minus b norm square. We have this. Yeah, still fine because we don't change anything with the constraint set. Now I want to remove yt plus 1 from this. Okay, so how to remove yt plus 1? So to remove yt plus 1, I will use the property, one of the property of projection. More precisely, I want to use the second property of projection. And this is the second property of projection because xt plus 1 is basically the projected point of yt plus 1. So using the second property of projection, we have this inequality. Okay. So from this, how can we make this inequality? First of all, this one just gamma over 2 times gradient of fx t norm square, and xt minus x star square just I write down again. And for this yt plus 1 minus x star norm square, I use this inequality. So I replace this one by this summation. Okay. So in the end, what's the difference thing compared to the unconstrained case? Everything is the same, but only this part is added. Minus 1 over 2 gamma yt plus 1 minus xt plus 1 norm square is added to this vanilla analysis. So here, good thing is this one is negative, right? This one is negative, and we want to make an upper bound for fxt minus fx star, which means we can simply ignore this. So now we have this one, fxt minus fx star less than or equal to gamma over 2 times gradient of fxt square plus 1 over 2 gamma xt minus x star square minus xt plus 1 minus x star square. This is exactly the same. So we have the same result. Sum this up over the iterations t. We have this, and we have this as before. Nothing changed.